Hi, my name is Jason. On behalf of my co-authors, Jeremy, Weisong, and Christoph, we present SafeSpect, Safety First Augmented Reality Heads-Up Display for Drone Inspection. Drone inspection has become increasingly important for maintaining the urban infrastructures, especially those hard-to-reach areas. However, in the densely populated urban areas, the drone pilots need to maintain situational awareness at all times to avoid causing damage in the mid-air or on the ground. The current tablet-based interface for drone inspection often reduces situational awareness and causes attention tunneling. The drone pilot often focuses on the screen rather than the drone's physical surroundings, which increases the risk of collisions, and switching attention between the handheld controller and the real drone causes additional cognitive load. The heads-up augmented reality interface addresses these issues by overlaying camera feed into the pilot's visual line of sight, as well as displaying in situ 3D visualization to help locate the drone and track the mission progress. However, presenting multiple critical elements such as battery, GPS status, speed, and control status on the interface without overwhelming the pilots remains a key design challenge, especially when considering safety-critical scenarios such as GPS loss, wind turbulence, critical low battery, or mid-air obstacles, which could cause information overload and lead to decision-based errors and drone accidents. In our research, we investigate two research questions. Firstly, how can 3D heads-up AR interfaces reduce the cognitive load of the drone pilots performing facade inspection? Secondly, what design factors on the heads-up AR interface can ensure safety and situational awareness during critical scenarios of the drone flight? To understand the practical workflow and challenges of drone-based building inspection and identify the design requirements, we used the participatory design techniques to generate design concepts. We recruited 5 professional pilots from the French Civil Aviation School. Together, we identified 3 cognitively demanding challenges during a drone inspection mission, including the split attention between safety signal monitoring and data acquisition, battery life management, and dealing with GPS loss and drifting issues. Furthermore, we used paper prototyping techniques to generate design ideas. We categorized the findings into 3 themes. Firstly, pilots mentioned the importance of using AR to enhance safety, such as showing the heading of the drone, visualizing the drifting direction and the danger zones, using colored line to indicate the spatial relation of the drone and the surroundings. Secondly, AR can be valuable for tracking the mission to improve usability, such as highlighting coverage over the building surface, showing the past and future mission trajectory, or displaying the marked points of interest. Last but not the least, pilots proposed to balance the mission and safety information so that the complexity of the interface can be reduced. Additionally, pilots suggested adapting the camera feed's placement depending on the control mode. Based on these suggestions, we focused on the concept of adaptation between safety and mission tasks using iterative design study approach. We developed a VR-based drone inspection simulator to test different heads-up AR interface design. The simulator features realistic building inspection scenario based on the city center of Singapore. We rendered 6 types of defects with custom textures, and the mission objective is to correctly spot all defects on the building facade. The simulator starts when the user takes off the drone. A green AR area effect is displayed to indicate the takeoff and landing zone of the mission. The pilot then needs to manually fly the drone inside the mission boundary, which is visualized as a green boundary over the building of interest. The locator ring and the drone heading helps the pilot to notice the position and orientation of the drone. The ground projection helps to gauge the height of the drone. After entering the mission zone, the boundary is hidden and autopilot can be enabled. The entry waypoint is highlighted to indicate the starting point of the autopilot. When autopilot is enabled, the AR control elements are hidden and the interface becomes mission-focused. The coverage indicator will be generated when the drone stops at each waypoint, and the pilot can mark the defects by clicking on the camera view. When a nearby obstacle is detected, the interface is adapted to a safety-focused view. The collision detection is visualized on the drone to enhance the surrounding awareness. We also implemented a head tracking feature, which hides or reveals the 2D interface based on the eye gaze. During the GPS loss, the interface is again switched to a safety view with GPS uncertainty displayed under the drone. We simulate the GPS loss by emulating the wind drift and the visualization drift on the drone. When the battery is low, the return to home path will be displayed and colored in yellow, indicating the need to perform manual or auto landing. As shown in this figure, the battery's efficiency over the 3D path is similar to the battery slider on the 2D interface, helping the pilot switch between two interfaces. A critical low battery is signaled by a red bar on the return to home path. We refined the concept and the behavior of the adaptive interface in our iterative design. The mission view focuses on inspection during autopilot. The 2D interface is centered in the pilot's vision, with most interface elements hidden, showing only the status message, 3D path, and coverage information. On the other hand, the safety view focuses on manual piloting and the visibility of safety issues within the line of sight. The 2D interface is body-locked to assist line-of-sight piloting with drone-centered visualizations. The system automatically switches from mission view to safety view when emergency events are detected, including near collision, GPS loss, or low battery. The pilot can return to the mission view by enabling autopilot when no safety issue presents. To evaluate adaptive design and gather more qualitative feedbacks, we conducted a comparative user study using our VR drone inspection simulator. The study involves 15 participants who have prior experience with outdoor drone flight. We compared three types of interfaces: a 2D tablet-based interface, a static AR interface with full visualization, and our adaptive AR interface. The results show that while the performance was not affected, the adaptive interface significantly reduces cognitive load and improves situational awareness. And the AR interfaces in general improves the safety information accessibility and the confidence of using the interface. Lastly, the semi-structured interview reviews several insights that can be used by designers of heads-up AR interface. To reduce the cognitive load of the AR interface, designers could reduce the complexity and enhance the attention switching efficiency of the interface using the adaptive design. Besides, the clarity of the visual cues can be enhanced by increasing size, enhancing contrast, or using eye-tracking methods to emphasize key elements. To allow controlling the drone both manually and automatically, the interface needs to clearly delineate signals and actions required for transitioning between the two control modes to streamline the operation. Furthermore, the designer could include customizable options for interface placement, content, and interaction modes to enhance usability. To safely deal with critical scenarios during the drone flight, two key points are highlighted. Firstly, the interface could enhance the transparency of the adaptive behavior by explaining the rules and triggers behind. Secondly, the saliency of the safety warning could be further enhanced by using distinct visual or auditory cues without obstructing the direct view of the drone. Thank you.